everyone, my name is Amir, and I'm going to talk to you today about CAP Theorem Reloaded and how to optimize your distribution of telemetry data. Telemetry data specifically constructed out of logs, metrics, and traces at scale. And CAP Theorem is an interesting mechanism. We're talking about consistency, availability, and partition tolerance. And we're going to use that framework to analyze and look at this distributed system that is comprised of telemetry data. So I'm Amir, as I said, and before co-founding Sawmills, I was VP engineering at New Relic for 5 years. Over there, I saw firsthand the tremendous amount of data that companies need to deal with from all the observability, all their agents and infrastructure and whatnot. That became a huge problem. And I decided to co-found Sawmill. And over there, what we're doing is helping a customer get full control of the telemetry data. Everything that we do is based on the OpenTelemetry collector. That's been we believe it's a huge tool that is not leveraged enough. CAP Theorem, we want to analyze our distributed system through that lens, so we need to understand what CAP Theorem means, and later on we're going to talk about what CAP Theorem means in telemetry data, in overall in OpenTelemetry as we define it. So CAP Theorem is very interesting construct comprised of consistency, availability, and partition tolerance. Consistency is making sure that when you request some information, let's say you want to read logs, and you go to Loki to retrieve those logs, and you query them once, it goes to one node. Let's say you query it again, and it goes to another node. Data is going to be consistent. You're going to get the same amount of data, no matter where you query the data from. So that's consistency. When talking about availability, you want to make sure that when you send a request, no matter what's going on with the nodes, there's always going to be a node that's going to respond. System data is available, and the system can respond to requests without responding with errors. Partition tolerance is the most interesting in a way, because it's frequently what's happening all the time. It's what happens if part of the systems are disconnected. And in many cases, you actually want that up front. You want part of the system to be disconnected. You want systems to be stateless. So it's about how the system behaves when part of the system are disconnected, but also what happens when a pipeline, a flow is disconnected in the middle, and you kind of got to figure out how to still serve requests and how you deal with what happened when the network comes back. Now, academically, I think 20 years ago or so, I don't remember exactly when that was defined, that you can't have it all. You cannot have, it was proven, you can have a distributed system that is both consistent, highly available, and is partition tolerant. You gotta compromise, and then you can choose 2 out of 3. So you can either have consistency, availability, or partition tolerance. You gotta pick 2 and compromise for 1. And there's a lot of interesting trade-offs here. There's a lot of also caveat. There's things like eventually consistent that you can do while compromising for consistency. I think it's a very strong mechanism to analyze a system and understand how they perform and how to fix issues that might come when you design your observability, your full telemetry posture and observability solution for your company. So we talked about CAP Theorem in general, but what does it actually means for telemetry data? So consistency, we want to make sure that the backend, so you have a pipeline, you have got agents that collect logs, you have some pipeline in the middle, let's say OTel collector, vector, or something else. And then at the end, you have some storage mechanism and some system that can query that storage mechanism. When we're talking about consistency, telemetry is making sure that you always get the latest data in real time or closest to real time, that you can trust your dashboard, you can trust your traces, they're complete, you don't have any missing pieces in the middle. And I think the most very important thing to think about is you have the sense that you have all your data, and that's I think we're going to talk about it a little bit more. And I'm trying to seed something here that you don't necessarily need all your data. You need all the relevant data. You need to feel like you have all the data. So if you have any data that is not necessarily relevant, I wouldn't consider that consistent in telemetry. Maybe in CAP Theorem, that's not considered consistent. But here we're talking about what do we actually need in real world to be able to analyze my system and really solve problems that telemetry data is coming to solve. So eventually think, is the data I'm seeing the whole true? Do I really understand what's going on in my system? And that's consistency. Availability is in telemetry data means you can always get the data that you need. So the pipeline is working, the agent is working, and the storage is working. It's very close to what is defined in CAP Theorem, but you also need to think about what's going on with the system. It's not working. When there are networks, and what are you going to do when there are problems? Because eventually you can't have, when you have an incident, you have to make sure that your telemetry data and your observability system is still working to be able to investigate that issue. So that's availability in telemetry. Partition tolerance in telemetry is something I touched on before. We're talking about what's going on when there's some disconnect in the pipeline or between different components. Now, because mostly in telemetry data, systems are stateless until you get to the storage, we're mostly talking about disconnect in the flow of data and not necessarily in components that are at the same layer that are adjacent to one another. So what you got to think on here is how you're going to buffer data. Should you buffer data? There are problems there as well. Are you going to create find ways to distribute the data in a way that if there's a networking issue in one node, it's going to use a load balancer and set it data elsewhere. So basically what happened when network is not available, some entity is not available, and there's some disconnect. So as I said, CAP Theorem pretty much says that you can't have it all. But in our case, because of the nature of telemetry systems, usually network is the main issue, and partition tolerance is something that is very hard to achieve. In a sense, I don't even think it's possible, because you eventually, when you think about it, the relevant part, as I said, is the stream of data. It's the pipeline. It's not the adjacent parts. So if you have a disconnect, let's say, between your agents, your pipeline, and some observability system at the end that is a SaaS provider, and you're trying to send data out, but for some reason the egress doesn't work, there's no way around that. You're going to lose data unless you do something in the middle. And that's where you got to think about your consistency and your availability. When talking about consistency, it means we don't want to lose any data, right? So you got to be, it probably means you're going to either buffer and store data in memory, even store it in drive. And once the connection is back, you can send the data back to or forward to the observability system, and eventually you'll have that data ready to query when the network is back or when the incident in the destination is restored. Availability is a little bit more tricky in that case, but it's still possible. And I've seen it in some companies. You have backups. You have cases where you actually have another mechanism to query logs. So if, for example, the observability system, the SaaS provider, is down due to network or some other reason, you can always store the data also to S3 and have backup, and eventually have something like Athena to be able to look at the data. So you can drop, throttle, or sample the data if there's too much data, but you can also just store it in some backup mechanism to have it available, even though the destination is down due to some disconnect that, sometimes it's not out of your control. So we talked about CAP Theorem and explained what it means in general. We talked about what it means when talking and looking at the telemetry data and telemetry distributed telemetry systems. But usually you have in traditional system, you have agents and you have the observability platform, some SaaS provider or some open source on-prem sort of system that you're using like Prometheus. And you only have the ability to play and manipulate the data at the source or at the destination. And OpenTelemetry Collector pretty much changed that perspective and created a new way to think about the entire thing. So you're not limited anymore to manipulating the data at the source or the destination. You can do that using the OpenTelemetry Collector. I like to call it the Swiss Army knife of telemetry data. And there's a lot of different processors. So, OpenTelemetry Collector is comprised of receivers, processors, and exporters. Receivers are what support getting data and converting it into OpenTelemetry Protocol, OTLP. Processors are allowing you to configure and manipulate the data or filter it. And the destination or the exporters are what we use to send the data out. So you can send it to you through OTLP, or you can send it to tons of different platforms, from Datadog to Cortex and Loki and Prometheus and whatnot. Very easy to extend, very easy to work with. The interesting bit we're going to talk more about today are some of the processors. So in our case, we're going to talk more about filters. We're going to talk about sampling and probabilistic sampler, tail sampling, how to manipulate data, and using you can use storage, which is part of the exporter today. Like, I think batch processing is something that is going to become obsolete and move to more closer to the exporter, which makes sense. And the collector can also protect itself from out of memory errors using an extension actually called memory limiter, which is kind of interesting. Later on, we're going to talk about something that we extended in the collector, and I'm going to keep it to the end. So we want to manage our logs. As I said, we have a tsunami of data. There's just too much data that is getting, and we're talking about turning our system to become more consistent and highly available. But as I said, consistency doesn't necessarily mean you have all the data. It means you have all the relevant data to understand what's going on in your system. So in a sense, if you want your system to be more stable, you actually want to send less data. And you can do that using the filter processor. And I highly recommend starting to look at the data that you're getting through your pipeline and starting to filter out things at the source, or in our case, at the middle of the pipeline, at the collector level. And you can, for example, filter based on severity. I don't know a lot of companies that I don't think it's even considered a best practice to have debug logs, for example, getting all the way to observability system in production. If you're relying on debug logs, it's going to be very hard. You're going to have a bad day, as they say. So that's one very easy way to start. Attribute trimming in subsystems. You actually have attributes that repeat themselves. You'll see in most SaaS-based observability provider, they tend to extend logs and traces and metrics with a lot of bloat when it comes to metadata about the data, which is fine in many cases, but you'll see a lot of duplication. Eventually, it increases the amount of data that's being sent, increase the amount of cost you have, and you don't necessarily get better observability. You actually get more harder to read data. Sampling is something that is a must when talking about traces. Just too much traces to store. So that's something that, there's head-based filters, sampling, sorry, and tail-based. When talking about, we're not going to touch over that, but just a word. Main difference between the two is one is all about probabilistic sampling. So picking up randomly what traces are going to be sampled, what not. And tail-based sampling is all about getting all the traces, all the way to, let's say, the collector, and then the collector is going to pick which traces going to be sent to the destination based on criteria in the trace. So if, for example, the trace is interesting, it's going to be sent forward. If it's not interesting, it's going to stay. It's going to be dropped, basically. Super interesting, but that got a lot of problem all by itself. Managing tail-based sampling is, I think, a topic for many different talks. So not focused on this talk, but super interesting. So when talking about filters, we talked about what you can do in the collector, but you can also, and I mentioned that before, do that in the backend. You can do it by using various techniques at your backend. Splunk, for example, allow you to do tiering, so you have cold and hot and whatnot storage mechanisms. And when talking about availability, remember to keep your data and to buffer your data. If you're worried about networking, what's going to happen. But if you're worried about loss, you should store the data, not just buffer it. And always use more than one instance of the collector. And I don't think it's a good idea to just have one collector to hang around. It's something that just not recommended. Something else to think about, and I've seen that done, is trying to map the amount of traces. Map the metrics, metrics you have, and try to only pass on the metrics you actually need to build dashboards. So you don't necessarily need to have all the metrics in the world. In staging and in your production, you're in development environment, you can start with more metrics, and the lower you go, and when you go to production, you don't necessarily need those metrics. But there's a caveat here: you still want to have the data that you didn't think you need for incidents. So it's kind of tricky, but I've seen it done. So the same dilemma when it comes to metrics also happening traces, as I mentioned, head-based sampling and tail-based sampling. One is very easy, probabilistic sampling. Basically, you flip a coin using random, and that's how you can decide whether you're going to store some trace or not. But that basically means that you don't necessarily store the interesting ones. You don't know what's the distribution of problematic traces. And then tail sampling comes in, and that becomes much more complicated, but that provide you the better consistency, because you'll be able to see the data that you need. But it's impact the availability, because it's hard on the resources. And as I mentioned before, partition tolerance becoming harder in that case, because the data is not stateless anymore. You route all your traces to one node, and if that node is down, then you lose the entire trace. So tsunami of data, the real problem, we identified an interesting problem that is connected to the crazy amount of data. And think about it yourself. Would you, today, I don't think there's a good way to control the flow of data to your observability system. So if you have, let's say, 3 departments, and all of those departments send logs, traces, and metrics to some observability system, some SaaS provider, and you closed a monthly, there's a monthly payment that gets sent to that provider. How can you guarantee that that's not going to cross some cap? So basically, what you can do if you really want to is you're going to set a limit in that observability system. Let's say, I don't want to have more than 5 gigabytes a day that gets sent. After 5 gigabytes, I want the data is going to be dropped, or the data is going to move to a different tier. That's great. That's going to provide you with availability, but you're going to lose data that might impact your consistency. You might lose the data that you have. But another problem there is that you don't really know why is it going to be blocked. So you might have a noisy neighbor's problem, and you can't really do capacity planning. So you do that for the entire organization, entire company, but you don't really know which department is actually sending more data and which department is actually sending less, right? So what if you could actually manage that the collector? So that's something that we started working on. So doing that in the collector level, but generally speaking, there are other ways to manage quotas. So what we took the inspiration from is first the memory limiter that is already doing that, but on the collector level, there's the filter processor that you can use to filter out data and reduce the amount of data, but that doesn't really allow you to control how much data is going to flow through a collector, right? So you can manage the memory, you can filter out data, but you can't really say something like when it reaches 1 gigabyte, drop or do some action. When something happened, do something. And there's an interesting issue here as well. So what we've done and the problem that we had is that, let's say you have 3 collectors. That's it, simple system. You have 3 collectors, 1 observability system, and 3 departments, and you don't want you don't want a breach of more than 5 gigabytes. You want only 5 gigabytes a day for the entire department, and you want to divide it. You want one department to get 1 gigabyte, another department to get like 2 and 2 or something like that. The first problem is we said we have 3 collectors. So each collector is going to count the data by itself, so independently. So that's great, it's stateless. But it's kind of a problem when we're talking about global quotas, right? Quotas should be for the entire organization. It shouldn't be for a single collector. So how are we going to do that? On one hand, we need to manage it for each collector independently. On the other hand, we have the quota is global. And so on top of the collector, we designed a quota coordinator, and we manage the configuration for quotas through S3. So when the quota enforcer processor is loaded, and that's the name of the processor we built, data configuration is loaded from S3. Data is flowing from sources, goes through the processors, throughout like close to the end, it goes through the quota enforcers processor. And the quota enforcer processor is doing 2 things that I see as very interesting. First, it manages its own quota independently. So you still get data is still highly available, still partition tolerance, because it's not dependent on other states, and it's still but it's not consistent. And we're going to talk on that in a second. Metric gets sent to the coordinator, and the coordinator manages quota data through it counts the quota data from all the different collectors and report it back to S3. And every few moments, the quota enforcer is reading out the global quota and update it. So what you get here is an eventually consistent mechanism. And we're talking about quotas. It's okay to not be 100% accurate for availability's sake. It's more important to be available than to be 100% consistent, but you do get eventual consistency. So in other words, what you get is you're in an error margin window that is tolerable and data flow is still possible while still limiting the amount of data. So to reiterate, data flows through the sources, goes to the quota enforcer. The quota enforcer is checking whether I had enough data, whether we reached the limit or not. If we reach the limit, and we're talking about the simple counter that sits in the quota, we're doing what is configured by the system is going to do what's configured to do. It can sample, it can drop, it can store to S3 and drop. All the while, every once in a while, it gets updated on the global quota. So eventually, within error margin, we make sure that the quota is the global quota. So if you reach that like 1 gigabyte limit for a specific department, data is going to drop. And that's how you can get the ability to do capacity management through different departments. All that thanks to we implement on top of the collector, which I think is super interesting approach. So like talking again about like unpacking what I talked about here. So there are predefined policies or rules that we need to manage under resource constraint. We decided to prioritize availability. So we're talking about A here. We chose A. We want to make sure that even though part of the systems are not working, we want to make sure that always data is flowing, even if we can't read from S3, even when something is not working, like data would flow, count would happen on the collector level. So that's number one. We're also doing that thanks to the decision to compromise on eventual consistency and not necessarily on 100% consistency, which is very, very hard to reach in distributed systems. We decided to be able to handle partition tolerance, right? Like I think it's connected to availability. But basically when the system behaves incorrectly, when the network is done, the processor is still working. And what happens when the quota is on? Data is going to be dropped. Throttling is something that is possible. So you can say, I want a control amount of data in a window of time. And we can also notify the user when those quotas are breached or about to be breached. Key takeaway from today's talk, CAP is a great framework to analyze your telemetry based system and talk about what are you want to achieve. Are you prioritizing consistency, availability, and are you partition? How are you dealing with partition problems, with network problems? The OTel collector is a great it's the Swiss Army knife of observability, really. You can do a wonderful thing with it. You can extend it, all super performance. Highly recommend understanding and really learning to control the tool. Always think about whether the data that you need is valuable, whether you really need to store all the data, what data is really being looked at, what is impacting, what's cost effective. Are you really need to store all the data for the value it's presenting? I don't really necessarily think that storing everything in observability is a must. Think about what's important for your business when that thing. And last, I would encourage you to start thinking about leveraging AI. We're getting into a new evolution or revolution, depends on how you look at it. And AI is something we can't ignore. So I've been started thinking about summarization and dedupe and smarter sampling, and how can we introduce AI also to telemetry data and streams, and where that can be encouraged. A lot of that is things we're doing here at Sawmills. Yeah, thanks everybody.